The main thing I want to accomplish today is solving mazes, which is a separate problem from everything that we've done so far. So if this is your first episode, then I think it's a good place to start. So, items weird substance, which is obtained by fertilizing plants, has a strange effect on bushes. Okay, so we're going to have to figure out how fertilizing works. If the drone is over a bush and you call use item weird substance amount, the bush will grow into a maze of hedges. The size of the maze depends on the amount of weird substance used, the second argument. Without maze upgrades, using n will result in an n by n maze. For each upgrade level, you need an extra n to get the same effect. Okay? There is treasure hidden somewhere in the hedge. Use harvest on the treasure to receive gold equal to the area of the maze. Mazes do not contain any loops unless you reuse the maze. You can check if there is a wall by trying to move through it. Move returns true if it succeeded and false otherwise. For an extra challenge, you can also reuse the maze by using the same amount on the treasure again. This will increase the amount of gold in the treasure by one full maze. And move. Ooh, okay, that sounds really cool. Oh, I love that. Okay. Using measure on a treasure returns the position that it will move to as a tuple. Each time the treasure is moved, a random wall may be removed from the maze, so reused mazes can contain loops. Okay, so we definitely have to remember what the maze is if we're going to be doing the reusing stuff. Note that loops in the maze make it much more difficult because it means you can get to the same location again without moving back. Reusing a maze doesn't give you more gold than just harvesting and spawning a new maze. Okay, but if you know the full layout of the maze, then it's going to be quicker. I guess in principle it depends on measure. If you know it's moving to like a convenient location, you want to reuse the maze. If not, you probably want to start a new maze. This is 100% an extra challenge that you can just skip. It's only worth it if the extra information in the shortcuts are... Yeah, exactly. The same maze can be solved a maximum of 300 times after that using weird... Okay. So yeah, there's like the basic mazes, and then there's the advanced mazes, which is reusing the same one but with loops. So let's try and pick off both of them. I don't really know anything about how mazes work in general, except in real life, like if you put your left hand to a wall and you just keep following and keep your left hand on the wall, you eventually solve it. Because every time you go into a dead end, you come out on the other side, if that makes sense. So that's going to be our first algorithm, is just kind of following the left wall. Obviously it works for the right wall as well, but you know. We're going to need some of this weird substance, so let's figure out what fertilizing does. Similar to water, you will automatically receive one fertilizer every 10 seconds. I'm just going to work on getting ourselves some of the weird substance for now. So while not can harvest, we're going to use the item fertilizer. And then we'll check again. I guess we'll probably only end up using one, but this will do harvest fast, let's call it. And this is going to passively get us some weird substance, and we'll keep an eye on the fertilizer, whether we're going to run out of it or not. And if so, then we need to just change the balance of some of these constants. So utilities, instead of waiting harvest, we want harvest fast. Okay, so this is going to get ourselves some weird substance, so we can at least get a maze. How do we start a maze? Plant a bush, and then we get the world size. Num unlocked entities maze. Okay, yeah, so as you upgrade the mazes, there's more gold, but it costs more to build one. So let's call this def start maze. And let's run it. Okay, so we can't use this, and auto unlock is a while away. Actually, we can unlock dictionaries. They're definitely going to be useful. But we're never going to get dinosaur bones. So let's start ourselves a maze. Okay, so it replaces our farm. We stay in the same location, which is interesting. Maybe there's some optimization to be done there. It feels like it's probably better to start in the middle or a corner. It's going to be one or the other. It's probably not going to be on the outer ring that it's best to start. It's probably either the middle or the corner. And maybe we can measure and run like 100 mazes and see which is quicker. From here you can see if we were hugging the left wall, then we'd be going a very long way around. Oh, and then here we reach a dead end, we come all the way back, left wall, reach a dead end, and then we come all the way back, and then we get the treasure. So we actually take the possibly the longest route we could. But in doing that, we would build up a picture of the whole maze. And if we decided to rerun the same maze, then we could hopefully just go straight to the right location. So let's start building this hugging approach. So take treasure if possible. So if get entity type equals entities treasure. What do we do? Harvest. Else do nothing. Let's just test this take treasure if possible function. So let's manually solve the maze, see if it works. Move north, move west. Can you do 2? No. Move west. Take treasure if possible. So this should solve the maze, and then we'll see what happens after that. Okay, so then we go straight back to a blank farm, so we'll have to start a new maze at that point. So let's get ourselves another maze to play with. So we know that take treasure if possible works, so that's good. We now have a new maze. We need to try and move, and we're always going to be moving with our hand on the left. So in this case, what does that mean? So we've got our hand, say, on this left wall. The most left you can move is going to be, say we're moving upwards at this point in time. The most left we could move is west. If that doesn't work, then we need to move north. If that doesn't work, then we move east. I'm bad with my directions. I think it's as simple as that. We just kind of have like a direction order. Do we have lists yet? Lists are unlocked. So we'll have a direction order, which is going to be, so the most left is going to be west, then north, then east, then south, and then we'll have like this is probably a constant, right? So we'll have a move 1 step while okay, so I want to do like while can't move. I guess we do it with a for loop over the direction. So for direction in direction order, if move direction, then we break out. Otherwise, we're going to go to the next direction and try. So I think if we move 1 step now, it should try and move west, fail, try and move north, fail, and then it should move east. Let's add some print statements. So quick print. Can I use F strings? Probably not. Trying to move direction. Do we have F strings? Debug. Oh, breakpoints. Yeah, breakpoints would be very useful for this actually. And let's make that return true when the maze is solved. Otherwise, return false. So then we can do. I'm getting so far ahead of myself, but I feel like we've solved the mazes, so I just want to go for it. So while we haven't taken the treasure, then we're going to move 1 step, and then we'll use some breakpoints and step through it. So executes 1 step of the code, runs here. Okay, so we can't print like that. How does print work? Maybe you just do like that. I'm trying to move in that direction. And I just want to make sure that this isn't going to solve the whole maze. So debug breakpoints, when you it will automatically, okay, cool. So I can run this. Oh, okay, so this doesn't work. Nice. Why? Where are our prints, by the way? Where do they go? Quick print prints a value, but it doesn't stop to write in the air, so it can only be found on the output page. Where is the output page? That's going to be useful to have around. So this didn't work. Why did it not work? So we try and move west, but we couldn't. Then we try and move north, but we couldn't. Okay, so now it's going to try and move west again. But actually, because we're already moving east, our left hand is actually now on the north wall. So our new direction order is going to be east again, and then south, and then west, and then north. Does that make sense? So, because we've already committed to moving this direction, we have a new direction order. I think we can do this by indexing into this list. Let's see, how do for loops work in here? Do we have multiple types of for loops? There's that one. Do we have the range one? Yes, we have the range one. So the first time around I want to go west, north, east, south. Next time around, because east worked, I want to start with east. we'll have our current direction index is 0. And then for I in range 4, which is going to go from 0 to 3, then we will get direction to try is going to be the direction order indexed into our starting offset, current direction offset, let's say. Direction offset plus I, and then we're going to have to mod all that by the length of direction order, which I could put the constant 4 in there, but it feels nicer to do the length. So this is going to try this direction instead. And then obviously we can't do move one step. We'll just have to like solve in one go because we need this state. Let's do if move return current direction offset. Let's pull out the index. So direction index to try is going to be this, and then we do this. And then return that. And this should always return. But if it doesn't, can we raise exceptions? Can you raise? Let's do print something terrible happened. Hopefully this never happens. If it does, then we need to fix some bugs in this code. So this is going to return the direction index to try that worked. So the current direction offset is now going to become a parameter here. And then we're going to move one step. Let's say def solve maze. Current direction offset equals 0. I don't think we're hugging left anymore, by the way. I think we're kind of hugging randomly depending on what just happened to work on the first cell. But not too worried about that. So the first time around, we're going to start with a direction offset of 0, which is going to go west, north, east, and south. At some point, that's going to succeed and return, well, in this case, it's going to return west, which would be 0. Yeah. And then next time we want to try west again. Oh, I feel like we still might be looping, but let's see what happens. Let's see what happens here. So we'll try solving the maze. And we'll do a breakpoint here. Oh, sorry. That needs to be direction index to try. We definitely need to keep track of the direction that we're moving in. Direction to try. Yeah, okay, so we are still looping. Cool. Okay, we've made a bit more progress. Instead of moving 2 cells, we're now moving 4 cells. I guess we need to keep track of which side the wall is on. Yeah, okay, so let's forget this direction order idea for now and say like, so let's find a wall. So for direction in direction order, if not move direction, return direction. So eventually we won't be able to move, and that's going to find us a wall. So solve maze now. Wall side is going to be find a wall, and we'll print wall side. And this should print west. It does print west. I prefer the print, by the way, to the output thing, so I'm going to get rid of this, and we don't need to quick print when we can't even solve the maze yet. We kind of have a preference order of where the walls are, because we're going to move up north and then find a wall on the north, which means we want to move east. Find a wall on the east means we want to move south. Find a wall on the south means we want to move west. And eventually there's no wall on the south, which means we want to move south. So our bias is to move towards the wall side, I think. Let's have like get next direction wall side. And I think this might depend on where we've been as well. But for the moment we know that I'm going to turn these into dictionaries at some point, by the way, but for now we're going to use if statements. So if the wall side is west, we want to move north. Do that. And then next direction, get next direction wall side. And then we're going to try and move in the next direction. If we can move in the next direction... okay, yeah, so if we can move in the next direction, we've moved north in this case. We want to try west again. If not, then we do north. It's always like the previous value in here, I think. Always the previous value, and it wraps around. So if we move in the next direction, then we want to jump back to the wall side. Oh, here's something. We have to keep track of the wall side, because depending on what state we're in when we're in this cell, we can either move right or down. And in the worst case, we need to explore the whole maze, which means knowing our current location isn't enough info to solve the maze. You need to know the current location and whether you're trying to go anti-clockwise or not. So we definitely need this state to hang around. We definitely need to know what wall we're on. Based on that, do we just want to always try and go to the previous direction? So current direction offset -1 with the same code as before, while we haven't solved the maze one step. What does this do? Okay, that works. Okay. Right, can I explain what just went through my head there? I'm not sure. It turns out we don't need this, and it does work. Let's put another maze out there. Start maze. So, what was the insight? The insight was that you're hugging a wall, and the whole point is that you want to move in the direction of the wall, but you're not allowed to move in the direction of the wall while the wall's there. So you need to identify the moment in time where the wall disappears. Say you're moving north because there's a wall to the west. You need to keep trying west until eventually there is no wall to the west, and then you keep moving west, and then you keep traversing in the same order. Yeah, I guess this is the simple algorithm. Let's just try and solve a bunch of mazes and see if it actually does work in general, and then we can move on to reusing mazes, I guess. Yeah, this seems to be working well. It's not super satisfying, I'm going to be honest, because I just kind of put -1 in there on a hunch, and it turned out that it worked. So I think we're going to have to think about reusing these mazes. What's this saying? I guess we've run out of weird substance. So let's add mazes to our framework and then run it for a bit, and we should balance out our resources. Let's just always do mazes if we can. So if num items weird is greater than or equal to the required weird substance, then we're going to start and solve maze. And then I guess we do elif for these things. Yeah, and we need to import that. So from mazes import start and solve maze, and we're going to rename mazes. Alright, does this add into our framework? So we don't have enough power, so we're going to do some sunflowers. This is going to get us weird substance, which should give us enough to solve mazes. So next time we solve a maze, we still have weird substance, so we're going to use it all. And then we go back to the other stuff. Okay, so this is going to build up our gold. It's not going to be even like the other resources, because mazes work a bit differently, but it does kind of slot in. Yeah, so let's think about what we're going to do about mazes. So yeah, we've got the brute force approach where we're always traversing around, but I think the idea of reusing the maze is the cool thing. So we're going to need to keep track of where the walls are, and then measure where the treasure is going to move to next, and then go directly to where the treasure is. So algorithms for that, I mean, we need a data structure to store the hedge locations, And then the algorithm for solving the maze is like A star, or I guess we can do something a bit simpler. We can do A star would be faster, but I don't think we need to worry about speed. We just need to solve it. So I think we can use like a flood fill sort of algorithm. But I don't know if I can do all this stuff off the top of my head. This we're gonna have to see whether this is viable. This is the first challenge in the game where I've been quite intimidated by the prospect, but I'm not a quitter. Let's give it a go. So I've collected some weird substance so that we can test on some mazes. The first thing we're going to need to do is build up this data structure of where the walls are. Let's call this maze as simple and start working in a new code block. So this is maze as simple. I think the first thing to do is to traverse the whole maze, build up the picture of where the walls are, and if we see the treasure, we don't care. We're not going to take the treasure, we're just going to build up a picture. So def traverse maze. We'll have our starting... I guess we could move until we get to 0, 0, and then traverse the maze. And then we're always based on 0, 0. Is that going to be easier? That feels like an easier way to approach this, rather than starting in a random location. And at every location, we want to see what direction the walls are. And I think we can do that with a tuple. And we'll do it kind of inefficiently to start with, and we'll see. So get walls at current position. And this is going to return a tuple of booleans. So it's going to be like bool, 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 bool. I don't think the type hint syntax works in here, but the idea is it's going to be true if there's a wall to our west. Maybe you should always go northeast, southwest. I think this should still work. Northeast, southwest. It's going to be true if there's a wall to our north, east, south, and west, and false otherwise. So we're going to move wall north is going to be move north. I guess it's not move north. So if we move north, then this is true. We've moved north. And then this should be false because there's no wall. And then if there's not a wall north, we're going to move south again. And then we want to do this for every direction. So let's have, we have like a direction order. We kind of want a like opposite direction map. So like let's do opposite direction. And that's going to be a dict. So the opposite direction to north is going to be south. East is going to be west. South. It's going to be north. And west is going to be east. So that's our opposite direction. So let's import that. So from maze utilities, we want direction order, and we want opposite direction. So for direction in direction order, I guess we return a list. Let's have a wall list. So walls is going to be like that. For direction in direction order, we're going to is there a wall? Is there a wall? And let's use like programming things. So like wall in direction is not move in that direction. And then if there is not a wall, we need to move back. So we're going to move in the opposite direction to the direction that we tried. And then we're going to add that. Maybe this wants to be a dict. Just in case we ever decide to change the direction order again, instead of indexing it and assuming it's the same order, we'll set this to be wall in direction. And then we'll return that. So when I run this code, get walls at current position, I'm hoping that it's going to say west is true, south is true, and north and east are false. So let's do that. Can I print a dict? Let's find out. Get walls at current pos. For direction, that needs a colon. Okay, we can print north. I think that was okay. Let's do quick print and get the output. How do we open this? Outputs. North false, east false, south true, west true. So that seems to be working. That's going to give us the walls at every position. So now we need to traverse the farm, traverse the maze using move one step, and this time we're going to keep track of where the walls are. And in fact, I think as long as... Yeah, I think we don't need to worry about moving to the origin. I think we can do this from anywhere as long as we end up in the same location that we started in. So let's do that. So def traverse maze and identify walls. So we'll have a starting position, and that's our get pos tuple. And then while our position is not the starting position, we're going to move and find the walls. So we move one step, which is this stuff. So instead of it being to the origin, we traverse, instead of it being the origin, it's going to be the starting position now. We get the walls at this place, so let's have walls at position, and that's going to be a dict as well. And we say the walls at position, our current position, is equal to get the walls at current pos. Yeah, so that's going to store the walls where we are, and then we're going to move one step, and then we're going to store the walls unless we got back to the same location that we started in, but that's okay because we've already stored those walls. So that's going to give us a massive dict that's going to be a dict from a position and the walls around every position. So let's do walls at position. And then here, I think we will quick print as well so that we can see all of this data. So traverse maze and identify walls. This should, hopefully, move around the whole maze and identify all of the walls. So let's see. It didn't move at all. Move one step. Okay, so the first time we definitely need to move. Do we have a do while loop? Do? We don't. Well, let's try it. It doesn't seem like we have a do while loop, but let's see. If we did have a do while loop, okay, that's not highlighted. Then we would run this first. We'd be at a different position, and then we could move on. But I think we just need to do this so that we always move at least one place. So what's this going to do? That does move everywhere, and you can see there's some jitteriness because we're trying to find all the walls at every location. Ah, okay. We didn't manage to traverse the whole maze because we got back to the origin sooner than we expected. What did we output? So at 0, 0, north false, east false, south west true, 0, 1, north false, east true, south false, west. Okay, so that's working, but it didn't get all of the data. So we need to make sure that this actually covers the whole maze, and the easiest way of doing that is going to be to see the size of the walls at position. So if the length of walls at position is less than the size of the farm squared, do we have things like pow? I guess like star 2. So if we haven't seen everything, then we're going to get the walls at, and that's going to work at the origin. So let's see what this does. This should hopefully go straight past where we are. Yeah, and it does. And then it finally ends up there. Ah, because there was this tiny little one they needed to check, I guess. Let's see, output. So this, okay, it's truncated, but this did cover the whole maze. It's interesting we ended up in this particular location. It doesn't really matter where this function ends us up, because we're going to have to be able to move generically throughout the maze anyway. And we know for sure that walls at position has enough entries, because it's got the whole world size. Okay, so where are we at? We've got a function that traverses it and tells us where all the walls are. Now we need to actually get to a destination. So we need to keep track of what the destination is, which we probably need to do in our first traversal, but that's simple, so we'll do that later. And then we also need to be able to build a path. And the easiest way to build a path is to essentially try every direction that we can go into at a certain location. So at the location that we're at now, we could go north, east, and west. So we'll start building paths that go north, east, and west. And then from there, we're going to try and move every location we can from north that doesn't go backwards. And every location we can from east that doesn't go backwards, which is going to kill that path. And then the same from west. So we're going to kind of constantly build out every path until we reach the destination. Let's say for now that our destination is going to be 2-2, which is this cell here. Because I know that it's easy to find the location of the treasure and we can put that in later. The main challenge is building the path that we want to follow. So let's see. So we have all the walls. Let's say our destination is going to be 2-2. There's a few different ways we can do this. We can do the recursive way, which might be a good option. Feels like the recursive way might be the way to go. I haven't done this sort of algorithm for a really long time. When I was a kid, I used to enter like programming competitions and we'd do these sorts of things, but I can't for the life of me remember how you do this. So let's see. From memory, it seems like a recursive algorithm is the way to go. So let's try. Let's call this foo, which is what I always do when I'm not quite sure what a function is, but I kind of have an idea what I want to do and I just want to get some code running. So we want our current position for sure. No, let's make this a parameter. So let's say we're in a certain location. So let's call this find path, and then we'll have a target and then a current. And then what we're going to do is we're going to build longer and longer paths. So imagine that our target is 2-2 and we're directly next to it. This is going to return a really short path. But if our target was a little bit further away, then we would... I'm just going to write it down because it's going to be easier to write it down than explain it. So find path, target current. Okay. And then we're going to need our state, which is going to be the hedges walls. So we're in the current location. Let's say walls around current is walls current. If we can go directly to the target, then we're going to do that. So I think we need a distance, and I think we want the Manhattan distance, which is the it's just like, instead of the Euclidean distance, which would be the straight line distance, the Manhattan distance is like if you're going around blocks in America. The distance between here, where we're at, and this cell up here would be 1, 2, 3, 4, whereas the distance via Pythagoras would be shorter than that. So let's add a utility for that, and let's say def Manhattan distance between pos 1 and pos 2, which are going to be tuples. It's going to be the absolute value of pos 1's x coordinates minus pos 2's x coordinates plus the absolute value of pos 1's y coordinate and pos2's y coordinate. So this is the Manhattan distance. This is going to be the main thing I'm looking for is I want it to be 1. I want it to be right next to it. So if the Manhattan distance between us and the target is 0, let's say distance to target, if the distance to target is 0, then we're there. So the path is nothing. Else, if it's 1, this is the main thing that we're going to implement. We're 1 away. We could, if we're 1 away, say we're at 2, 2 right now, this location here, 1 away could still not be accessible. So that's not necessarily gonna get us there, but it might be. So let's see. If we're 1 away, then let's see which axis we need to do. So if the target x equals the current x, then we're moving north or south. So if target y is bigger than the current y, then we want to try and move north. So if walls around current north, so if there's a wall up there, then we can't do it. So that's going to return no path, but actually it's different to this no path. This no path is no path because you're there. This no path is we need to find another way. So to do, what happens here? Else return north. And then I think all of this is basically the same thing. We could probably tidy it up to not have to duplicate this code, but let's just implement it and then see if there's opportunities later. If the target is to the north of us, then we go north. If the target is to the south of us and there's no wall, then we go south. Otherwise, we do the same stuff. I think that's the main backbone of a recursive algorithm. What we need to decide is how to handle, okay, we're more than 1 away, and we're 1 away, but we can't actually get there. So in those cases, we need to try and find path with a different location. And probably we just go for everything. These are our base cases, right? If we're there, we're there. If we're next to it, then we go for it. Otherwise, I think we go in every direction that is possible. So for this is going to be so much code. We definitely need to simplify this. So for do we have direction order? Yeah. Let's do shortest path is none. Shortest path is none. For direction in direction order, we are going to try and go. So if not walls around current in that direction, if there's not a wall, then I was just thinking if we had to do anything special about the edge of the grid, but thankfully no, because there's always a wall around there. So we can just add to our coordinates. So let's create ourselves a utility for that as well. So we need a def coordinates after moving, and we're going to start with a start position and then a direction. And then if the, like I say, I'm not going to worry about, well, I guess we could worry about wrapping around. So if the direction is, do we have switch statements? Switch, no. If direction is north, then return start position naught +1 modulo get world size, and then in it, put that all in a tuple with the original y coordinate, and then we do the same thing for every direction. I feel like it should be elif, even though we've returned elif direction, it's east. Let's do south because it's the most similar. And then we want the same thing for east, and that's going to be start position 0, and then east wants to move in that direction, and then west is the last one. And let's just test this. So coordinates after moving, and we'll start at say 4, 5, and we want to move north. So we expect 5, 5 to be returned by this, which it was. If we move south, it should be 3, 5. And then if we move east, it should be 4, 6. Sorry, 4. Yeah, it should be 4, 6. So this wants to be a +1, and this wants to be a -1. Okay, because we're at 4, 5, 0, 1, 2, 3, 4, 5, and then that wraps around. Okay, perfect. So that's all working. And then west should be 4, 4. Great. So we've got coordinates after moving. So let's import that up here. So maze utilities coordinates after moving. If there is not a wall in that direction, then the new coordinates in that direction would be coordinates after moving current in that direction. And then we're going to find a path from that location. Let's say path is going to be find path from, we have the same target, but we would have new coordinates and the same walls. And then if shortest path is none, or oh, it's not, it's none in, this is it equals none. If shortest path is none, or the length of the new path is less than the shortest path, then we return, then we set the shortest path to be equal to that path. And then we need to do that in all of the to-dos. So this is definitely a candidate for a function, but for now I'm just gonna put them in. And then I think we do the same here, right? We've got our base cases, so this should terminate. Okay, yes, not quite. Not quite, we don't want to return, we set the shortest path, but then we return the direction that we had to move into, and then follow the shortest path. So we need to keep track of the best direction. So let's see here, best direction. Best direction is none. And then we do the same thing everywhere. I don't think we need to worry about these things being none by the time we get out there. Logically, there should never be a none here. So I think we're good to just return, say, best direction plus the rest of the path. But I'm not 100% about that. I think there should be this should always be present, but there might be a bug. And if there's a bug, then it won't be present. Best direction, return best direction plus shortest path. And then the same thing here. Yeah, this thing definitely needs to be a function. And the same thing here. I hope this is right after I spent all this time typing it out. And then we return the best direction plus the shortest path. So what's the idea here before I run it? The idea is if we're close to the treasure, it's easy to construct the path. If we're further away from the treasure, then we just try and move in every direction and then find the shortest path from there. And we don't really care how you find the shortest path. The shortest path is just going to be find path. And what that's going to do is, like, at every stage, it's going to keep trying all of the directions until eventually it gets close to the maze, gets close to the treasure, where it can find an easy path, which is these base cases. I don't think this one's actually strictly necessary. I think it's really just this that's doing the work. Now, the way that I've just described it, it is a little expensive because we're not pruning all of these. We're going to try lots of different paths. What we can do is we can extend this algorithm to also have a heuristic for, does it feel like you're moving in the right direction as well? And that's how A* works. But let's just try and get this one working first. Let's see what happens. So we're going to get our walls, find a path, 2, 2, 2, and see if we can get ourselves one. So we have the walls, traverse maze and identify walls. Like I said, the destination for now is going to be 2, 2. And then we need our current location, which I'm just going to type in as well, so that we can test different things. So current location is going to be 2, 0, and then let's do quick print find path to destination from the current location with those walls. And it would be a miracle if this actually worked on the first time, because I've just written a lot of code without running anything. Target current walls. Let's see what happens. Let's see what happens. We need a... Okay, it's moving to identify the walls, which is good. Error. Manhattan distance has never been defined. Okay. I don't actually know how to spell Manhattan, so I'm just going to go with whatever this function is called here. So Manhattan distance, and then we need to import it. Let's get ourselves our output as well. Output. Okay, so yeah, we're traversing to find the walls. And then we stay here forever. Target 2, 2. Current location 2, 0. So what's going on? Why do we stay here forever? I could hop into the debugger. Let's think about it first. Distance to target. What is the distance to target? Let's have ourselves a little test. Let's have a new scratchpad. So from utilities, import Manhattan distance. So Manhattan distance between 2, 2 and 2, 0. What is that? 2, which is what we expect. Okay. If the distance to target is 0, return that. I think we're going to have to do the debugger. I was hoping that that function would just be wrong, but that looks correct to me. Yeah. So the first time around, our distance to target is 2. So we go down here. Best direction is none. Shortest path is none. We go through every direction. If there's not walls, so that's going to be northeast, west, we try and move in that direction. And then we find a path from those locations. I wonder if we have to do the pruning. Let's run it through the debugger and see what happens. Okay, so find path. We're trying to get constantly from 3.5 and 3.0. So what is this? So 3.5 would be 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 3.5, and 3.0. 0, 1, 2, 3, 0. Okay. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. World size is 6. 0, 1, 2, 3, 4, 5. So 0. Okay, so we're constantly trying to... I don't think we should be anywhere near 3.5, right? It feels like we're moving through this hedge downwards. So that means it thinks we can move south. Okay, so now we're in here. Our distance to target is 2. Yep. Our target is 2.2. Our current is 2.0. So let's step through this and find out which directions it's trying and whether it's moving through a hedge. Right, so direction now should be north. There should be no wall. So the coordinates after moving. Yeah, okay, we'll run through that. Coordinates after moving. 3.0. That's not correct. We're trying to move north. It's moving us east. Where are we? I bet people have known that this was coming and it was going to bite us at some point. Right, so if the direction is north, this is the x coordinate. This is the y coordinate. So if the direction is east, we want to increase the x coordinate. We want to decrease it for west, and for north, we want to go like this. Okay. Now, what does that do for us? I think we can remove this one and see if it actually gets us somewhere. So yeah, the head just seems reliable. That's a pretty obvious bug. I'm kind of optimistic about this one. We still do the same thing. Right, maximum call step. Right, so what are we doing this time? New coordinates, 2, 1. 0, 1, 2, 1. Yeah, 2, 1. Now, we try and find a path. This time, target still 2, 2. Current, 2, 1. All good so far. Walls around current. North, yes, there's a wall. East, no wall. South, no wall. West, yes, there's a wall. Distance to target is 1 this time. We're on the same x-axis, which means we want to move north. Let's see. On the same x-axis, yes. Target 1. Yep. Is there a wall north? Yes, there is. Sorry. Now we're going to try north, but there is a wall. Now we try east. Yep. New coordinates after east. 3, 1. Okay, that's good. I think this might be working, but it's just getting itself in a loop because it's moving backwards and forwards in the same direction. So let's say, let's ban it from moving back in the direction that it just came from and see what that does for us. So, banned direction. Path, find path. The banned direction here is going to be that direction. The banned direction here is going to be the direction that we're trying to move in. And we're going to say, oh, it's actually the opposite, right? It's the opposite direction to the direction we're moving in. So we're saying, if we're moving north and trying to find a path from north, you're not allowed to move south anymore. So let's try that. So opposite direction. We'll pass in all of the parameters and then we'll worry about actually enforcing the ban. Okay, and then here, same thing. Opposite direction. And then initially, banned direction, none. Do we have defaults? Yes, we have defaults. Initial banned direction is none. Now, every time we have a for loop over directions, if direction equals banned direction, continue. And I'm coming for you. When this works, this is going to be a function. Not allowed to go in the banned direction. Too much indentation. Okay, what does this do? What debug output would be useful for this? I think this actually should be useful. So let's try. This method doesn't exist. Ooh, but this looks good, right? It's trying to get from 2, 0, and then it does 2, 1. Then it does 3, 1. 0, 1, 2, 3, 1. Then it does 3, 2. Ooh, yeah, this is looking promising. And then there's a typo somewhere. This needs to be a comma rather than a full stop. Let's go. Oh no! The operator plus cannot be used on... Oh, it is none. It is none. Have I missed a return statement somewhere? It should be at the same level as the for. It's weird that it was kind of working most of the time. Let's see what the output looks like. So it tries to get from 2, 0, 2, 1, 3, 1, 3, 2, 4, 2, 5, 2, 5, 1, 4, 1, 4, 0, 5. Okay, then it gets it to a dead end and it's not allowed to move back. Oh, this is so good. Yeah, this is definitely working right because it's following this. And it's not spamming the logs with like tons of other stuff. So actually sometimes the shortest path can be none Right, this seems like a good opportunity to extract this into a function because we're doing the same stuff all the time. And then I can fix the bug once. So let's do that. What is going on here actually? It's saying if there's walls, that I think needs to stay in there because that's a special case that we're doing some testing on the coordinates. It's saying, this is almost like find path itself. This is, what is this? This is find path, I guess find subpath? Find shortest subpath. Find shortest. Yeah, maybe. Yeah, I think we do need this because the whole distance to target 1 thing is important. Although, do we? Do we need this? I'm not confident enough to just delete it. Is this enough? That might be enough. I'm going to keep that code around in case we need to put it back, because otherwise it'd be really painful. But that might be enough. Trying to get from this to this. If we're there, we're there. Otherwise, go in every direction. I think that's enough. And now we just need to worry about this going back thing. So if the shortest path is none, if the shortest path is none, there's no path that's doing the band direction. So we basically need to cut that off. So if shortest path is none, return none. It's impossible. And then this is none. If path is not none, hang on, let me think about this. So we're in this location. Basically, there would be a path, but it's just longer than any of the other paths. So we want to signal it's none from here, but don't worry because I know that you're going to try west from the starting location at some point anyway. So that's handled by this for loop. Is it as simple as returning none there? And checking if paths is not none and all of the other stuff? Let's see what happens. Right, here's what I'm going to do. I'm going to save it into a text file. If the shortest path is none. It keeps tripping me up because in Python it is none. Let's see what this does. Where's our output? Oh, that's a lot. Oh my god, has that solved it? So what happened before we look at the path? We go north. The path that we did before, we get to 4, 1, which is 0, 1, 2, 3, 4, 1. Then we go 4, 0, then 5, 0. At this point we hit a brick wall. This returns none, but that's okay. We're going to try other directions way back from the starting position. So then we try east. So we try 3, 0. 0, 1, 2, 3. We try 3, 0. That fails as well. That returns none, but it's okay. We move on to the next direction. Then we try 1, 0. And then that keeps going. And eventually we get west, west, north, 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 east, south, south, east. And that gets us to 2, 0. Oh my god, we've done it. So now we need to follow a path. Follow path. For direction in path, move direction. So we got the walls, we got a destination. Let's make our destination 0, 5. Find path. and then follow path. So yes, we find all the walls. It's gonna. I love the fact that we could delete all that code. I knew that there was something going on, but yeah. Oh, that's beautiful. Okay, so now we need all the plumbing around it. We need to find where the treasure is on our first traversal. And then when we solve the maze, we need to find where it's going to be next. So traverse maze and identify walls and treasure. Let's have treasure location. If what's treasure? If get entity type is equal to entities treasure. Treasure location equals get pos. I just realized we don't need starting position anymore here. And logically those two go together, and then this is part of the while loop. So if we're on top of the treasure, then that's going to be the treasure location. And then we store the walls, and then we move. So we get the walls and the treasure location. Okay. Def solve maze. Solve maze 300. What's the deal? You put more of your weird substance on it, right? For an extra challenge, you can also reuse the maze by using the same amount. Okay, so we put more weird substance, which we have some. So again, classic, I'm going to call it foo until I come up with a better name. This time we have the walls and the destination. And it's not called that anymore, it's called traverse maze and identify walls and treasure. Our current location, I'm just going to inline that. We get a path to the destination from getPos with the walls. Follow the path. I'm just going to run it once. I'm going to solve it once, and then we'll see what happens after that. We follow the path to the destination. We harvest. No, we don't harvest. We do the other thing. We start maze. Where's maze utilities? We plant. We use item weird substance. Get world size. Again, eventually need to add num unlocked. We follow the path, and then instead, we measure it. New destination. Measure. And does that return a tuple? Let's see. Yes, it returns a tuple. New destination is that. Then we use the weird substance on it. Get world size. And then we'll find a new path. Let's just do this a couple of times. Don't want to loop and do everything yet, because I just want to watch it. So now we can reuse the walls. So following it the second time should be way faster. So this is the first way around. Then we do, let's just call it destination. Then we use the weird substance, it moves. Then we find a new path to where it's moved to. We follow that. Find the new destination. And then let's just get ourselves there. This should build up a bigger reward, right? Let's see. Oh, I need to actually run it. Okay, so we're traversing, finding all the walls. We only have to do this once now. This time we should have also found the destination. Oh, so good. And you see it's removing walls. You know, oh my god. So we're still finding... Oh my god. There's more. We're still finding the... This is great. It's obviously an improvement on what we've done before. But we can take it a step further. When walls get deleted, it could open up a shorter path to the destination. In that case, we want to update our walls dict. And I don't think we want to traverse the farm all the time. But when we're following a path, we could look around us. I mean, our current way is actually kind of slow, right? Because we're checking whether we can move. Oh, but it feels like by 300, once you know all the walls are gone, that feels good. Yeah, let's try that. Let's try follow path. And this is now actually going to follow path and update walls. Let's see. This is going to return some new walls. So instead of just following the path, we're also going to inspect what happened to the walls around us. So let's see. So instead of moving directly, we need to use... What's that function? Get walls at current pos. I don't know if this is faster, but it feels like the right thing to do, doesn't it? Because they're removing the walls. They remove the walls to make it so that you can't just follow your left hand, but they also open up an opportunity. And potentially, you know, if this wall was broken, that could make some really short paths. So it feels like over the course of 300 mazes, keeping track of the new walls is worthwhile. Even if it's not quicker, it feels like the better, like the nicer solution, doesn't it? So walls get current pos is going to be equal to get walls at current pos, and then we move. That updates the walls every time. Now what happens? Oh, we can't traverse the farm necessarily anymore. We're lucky that that still worked because, yeah, okay, it didn't really work. Yeah, okay, let's kill our maze and start over. I think that's the problem. Because now the walls don't line up the nice way. Let's see. So how do we move north? Oh, I can just do clear, right? Yeah, and then from maze. We're going to run out of weird stuff, so I'm going to have to collect some in a second. Let's see what happens now. So this will traverse everything successfully. Follow path has never been defined, of course. So traverse everything. Path. Oh my god. I got so excited I didn't actually remember how to program things properly. I had like the solution in my head, but I didn't. You have to actually type it out. That's the secret. Get current pos has never been defined. Get pos. Yeah, so you see it's now exploring around. It was more jittery that time. It's exploring around it when it's following the path. This is going to come in more useful when we're at like 300. I think it was 300, right? You can solve 300 in a row. Maximum of 300. Measurable. Okay, we don't have to look at 300. Measure returning none is the main thing. So let's turn this into a for loop. Let's collect a bunch of weird substance. I also want to see what the upgrade is. Increases the gold and the amount. Now we want to test the algo. We don't want to make it more expensive for us to do that. So what's the for loop here? This is going to be solve as many mazes as possible. So we want to start the maze. Let's just assume we go from a blank slate. Clear, start maze. Maze utilities, start maze. Clear, start maze. And then we traverse the maze. We find... let's do can continue while, I guess, let's just do while true. I think we can break out. We get the path, we follow the path, and then the new destination is that. If destination is none, equals none, if the destination is none, we're done, which means we harvest and return. Otherwise, get item. How do you count items? What is it? We've got it somewhere here. Num items. Elif num items, that stuff, is less than world size. We don't have enough. Then we bail. So this is like an OR. So if we've solved 300 mazes or we've run out of weird substance, we harvest and return. Otherwise, we use the item and then we continue. Path walls, that updates the destination, that updates the walls. Does this work? Clear, start maze, get the initial state. We find the path. We follow the path. And then we find the new destination. I think this works. Let's try it. We definitely need more weird substances to try it for real. So let's get some. How much do we need actually? So world size is 1, 2, 3, 4, 5, 6. So to do a real run, we kind of need like at least 60 or more. But let's throw it in here. Main. Required weird substance. Let's say, I don't know, 10. 10. I wanna do lots of them. Let's collect lots of weird substance. Instead of mazes simple, it's now gonna be solve as many mazes as possible. Probably this one's to be clear. Okay, so we're going to collect some weird substance now with the sunflowers. Now we've got this whole thing working, there's probably more efficient ways to collect weird substance, but anyway, getting power and getting weird substance is good. We're going to do mazes when we hit 120, so one more run of these, we'll have 120, and hopefully we keep solving mazes one after another. Error, of course. Start and solve maze. Oh, I imported the function, but I didn't change what it actually does. Right, okay, so we're traversing, we're getting the state of the walls. Then we go. We're jittering, so we're updating the state of the walls. We found a gap here. Ah, error. Right, okay, so our recursive algorithm probably assumes the same stuff about no loops. And we've made life harder for ourselves by trying to update the walls. So I know for sure if we never updated the walls, then this would work. Is that true? Let's just verify that. And then if that is the case, then we can look in particular about what happens around loops. Yeah, so this code is now assuming basically that there's still walls there. Ah, we still get this loop. Is it just taking a long time? Could be. Maximum call stack. Oh dear, we're gonna have to do A star. Oh dear. So I think this would work. If there wasn't a maximum call stack. What's happening is we're exploring paths that are too long, I think. Which means we need to cut off paths early. Or we don't necessarily need to cut off paths because the path might be long. But we need to make sure that we're generally trying to move in the right direction. So instead of finding all of the paths that go east first, which in this case is going to take a long time to get there, and in fact, with the original state with no walls, I think it probably would never get there. We need to go east for a bit until it seems like actually going south from here would be better. Or west would be better. So, how's that going to work? Well, we have the distance, and we want to kind of prioritize our directions so that we're moving more towards the destination. So, from memory, A star is a fairly small adjustment to this algorithm, but let's try and work out what it should be. So, if there's not walls in the direction that we want to move, we're going to try and find a path and move there. Maybe we just prioritize these directions in the order that gets us... I don't know if doing it recursively is actually easier than... I think we need to maintain state. Let's see. We could work back from the destination. Find a path from the destination to us. Is that the same thing or is that different? Working back from the destination. I think it's the same problem, working back from the destination, but let's keep our eyes on that in case it becomes a useful tool. I think the quickest maze solving algorithm works backwards from the destination and forwards from where you are at the same time. And then when they meet in the middle, then you join those two paths together. But let's see if we can make the one direction work for now. So we already don't go in the band direction. I think we just want to move in... Let's try moving only in the direction that's closest first. Yeah, that seems promising because that's going to move south. And at any point, say we've moved here. Let's try that. Let's try always trying the closer one first, and then see if that gets us off the call stack limit. And then maybe if it doesn't, we need something even more powerful. So let's do let's say distances in each. This is called a heuristic in like A-star language, so let's call this heuristic in direction. That's going to be a dict, and then for each direction. If it's a band direction, we don't do anything. Otherwise, the heuristic in the direction would be the coordinates after moving in direction is going to be the Manhattan distance between the target and the new coordinates. And then the direction order now is going to be in size order of this. So is there a, what do we have on dictionaries? Dict pop to remove a key value pair. Do we have like sorted? I don't want to implement a sorting algorithm. There's only going to be 3 things in this dict, so let's do it. Let's say, list. We have append and insert index. So let's do this. Ordered directions. Can we iterate over? Yeah, we can iterate over the keys. So let's do that first, and then we say ordered directions for key in the heuristic in direction. Heuristic in direction. Let's call this dict. Then the heuristic in that direction is, we get it out of the dict, and then if the index to insert is going to be 0, while the heuristic in the direction is bigger than, we're gonna loop over the ordered directions, which is going to look like, I don't know, north, west. Maybe this has a heuristic of 2, 4. And then we come here, we've got east with 3. Index to insert is 0, while the heuristic in the direction is bigger than ordered, than the heuristic in the direction, ordered directions index to insert. So while the heuristic is bigger than, the heuristic in that direction, then we increment index to insert. Which is like that in Python, and then we insert it into ordered distances. Ordered directions. Insert at the index to insert direction. And we also need index to insert is less than the length of ordered directions. So this should give us the order that we prefer. And then let's not try and solve. Let's just try and solve. Let's see if it works. And I think some of this is not necessary anymore, but let's see what happens. So, let's run this. Oh, damn. This needs to start empty. I was just demonstrating. Let's put a breakpoint here. Okay. So what's our heuristics in each direction? North is 6. 1, 2, 3, 4, 5, 6. Should be 7, I think, shouldn't it? 1, 2, 3, 4, 5, 6, 7. Heuristic in east is 8 because that's in the wrong direction. South is 4 because we wrap around. Oh yeah, okay. It doesn't matter, but it's after moving, so that's fine. South is 0 because 4 because we wrap around, so it wants to move south, but it can't. I think that's going to be okay. We could handle going off the edge differently in mazes because you can't wrap around, but I think it's okay. And then west is 6. So north, it's going to try south first and fail. Oh, I guess we can add that in here as well. If direction equals abandoned direction, or there's a wall in that direction, then don't do anything. Yeah, let's try that. Okay, so now what heuristics have we got? We've got north 5 and west 5, so it shouldn't care which order we go in. What's it do? Oh, there was an error. What was the error? What was the error? Ordered, oh, it doesn't exist. Ordered directions. Right. Probably we don't need this anymore. Yeah, clear should work, right? Yeah. So now it's gonna traverse the farm, find all of the hedges. We want a breakpoint there. Now what are our heuristics? It should want to go west. Yeah, so west is 2. So it thinks west is more promising than north here, which is correct. So what happens if we traverse a bit further in the code? Order directions after the first pass. Can't hover over it. Goes west-north. That's the order that it wants to try, which is good. Yeah, okay. Keep going. Keeps wanting to go west, west, west. Why has it not found the solution yet? Why has it not found the solution yet? So it tries to go, maybe that wasn't the problem. This is still an improvement for sure. But perhaps that wasn't the problem. So we go west, west. There's no wall there. The coordinates after moving. Maybe we bail out. Maybe we should bail out here. If new coordinates equals target, return direction. Otherwise, we don't need to find more paths, right? We're there. Interesting, these lists are often only one element. From the beginning, we can go north-south, but most of the time there's only one. Nothing there. wants to go east, a bunch. Once it gets here, it wants to go south. West and south are the same. But it goes west first. Oh no, west and south were in that order, so it thinks west is better, yeah. This seems promising. North and south, it prefers north, prefers east, prefers south, prefers east. Yeah, so it's always moving towards the, it's trying to move towards the treasure first. This seems promising. Let's see if we run into the call stack problem with this. So let's get ourselves a bunch more weird substance, I don't know, 30. And then we'll keep that quick print, we don't need this print anymore. So I think the actual fix was this. Rather than calling find path again, we just bail out once we know we can move in a direction and it gets us to the target. But this is definitely better. It's going to cut down on the call stack quite a bit by always trying to move in the right direction first. We've cut this out, remember, so we're still always assuming that the full maze has got hedges. If this works, then we'll put this back and we'll try and take advantage of the shorter paths. Runs a bunch. This one seems like a hard one to solve. I wonder if the call stack only counts function calls, in which case we can restructure the code to not use a recursive algorithm, maybe? It's trying a lot of stuff. So this, it goes recursively and tries to find a path. It moves in the direction that it thinks is best, then it tries to find a path from there. Eventually it reaches a dead end, that's all none. And it's not allowed to move back. If current equals target, return that. Otherwise we try and go. We go in the direction that feels best. If path is not none, then we return that. Otherwise, we return none. How does this go? Ah, we still get tracks. This looks like a circle, right? This should not be happening because east is a quick dead end. North should give us a heuristic of east, which should get us there pretty quickly. This feels like a bug. What's going on? Trying to get from 1, 4 to 1, 2. Yeah, so 1, 2 is the destination. 1, 4, 0, 1, 0, 1, 2, 3, 4. Trying to get from 1, 4, then it goes north, then it does 3, 4, 0, 1, 2, 3, 0, 1, 2, 3, 4. Tries to go 3, 4, 3, 5. It keeps wanting to go north. 2, 5, 2, 4, 4, 5. Does this repeat? 1, 3 to 1, 2. 1, 4 to 1, 2. It does repeat. It should not repeat. Because once it knows how to get there one way, then it should remember that. Okay, maybe it's not banned directions, but it's banned positions. You're not allowed to go back on yourself. Let's try that. Banned direction. Let's say banned positions. And that's going to be an empty list. In Python, I don't think you're allowed to do this. It would have to be none. So if banned positions is none, banned positions is going to be an empty list. Let's try that. I don't want it to circle back on itself in any anyway. I don't really understand how it could have done that by not going in the same direction, but certainly with the ones with loops, then yeah, this is required, but for the ones without loops, I'm not sure. But anyway, so we're going to have band positions. New coordinates would be that one. How do we create a copy of a list? Empty list. Let's do def copy and add initial list new item, new list for item in initial list. Oh, in fact, do we have sets? It would be quicker to do this as a dict, so let's do it with a dict, as in more efficient. So if we do for item in initial dict, new dict item is going to be, let's just call it true. This is just a quicker lookup than using lists. And the new dict new item is going to be true as well. So band positions now is going to be a dict, and if you're in this dict, then we're not allowed to go there. But every time we recurse down, we can't use the same dict because that's going to mutate it. It has to be a new one for each subpath. So in this case, the band positions is going to be copy and add band positions. I can't assign it to the same name, or I shouldn't. Copy and add band positions. Our current location. So none of the paths that this does should go through this current location again. If direction equals band direction, if new coordinates in band positions, continue. So we don't put it in the heuristic thing, which means we don't put it in the directions thing, which means we don't need this here. Also walls around thing, we don't need this either because we've already checked. Let's see if that's good enough to prevent loops. It's really not. Trying to get from 2-0 to 5-5. 0-1-2-0. Yeah, then it tries 3-0. So it goes back to 2-0. Did copy and add not work? Copy and add did not work. This seems decent. It's not testing that many. Are we going to get into an infinite loop? No, I think the band positions was right. So why does band positions work but band directions doesn't? I don't know. That's a question for the comments. So let's see. Now we want to take advantage of the final thing, which is that the walls update. And I think now that we've done band positions, we should be okay on loops. But let's find out. I want to really get rid of hedges, so let's collect a bunch of weird substance. So let's do 50 mazes worth. Now, I think because of the heuristic and the band positions, then we should be pretty fast at solving these mazes. Definitely should be quicker than what we were doing at the beginning of the episode. It's probably worth incorporating the mazes into the overall framework and collecting enough weird substance. But let's see if maybe I'm getting ahead of myself. Maybe this still doesn't work. Okay, let's see if we can solve mazes and take advantage of the missing walls. If we can. I mean, the missing walls was... that was something I got way too excited about. And then it turned out that the original maze solving algorithm wasn't actually working. But this does seem to be working. Let's see, we should be taking... That wasn't the shortest path then, but it is a path. And because of the heuristics, it's just going to find a path that gets us there. So yeah, this seems to be working. We are solving mazes. We're taking advantage of the gaps in the maze. We've got plenty of weird substance left, which means hopefully when this is fully empty, then we should... Yeah, you can see like these walls existed right at the beginning, but they no longer are, and we're able to go straight through them. We could try and adapt this to find the shortest path possible, but I'm pretty happy having a infinite solving maze here. It looks a bit ugly because of the jitteriness. In a way, we wouldn't have to update we don't have to update all of the walls. We know for sure that the direction we're going into doesn't have walls, so that could reduce a bit of time. But yeah, for now, I think that's a good place to stop. So yeah, thank you. I hope you enjoyed it. If you do enjoy it, give the video a like. It really helps with the algorithm. And let me know what you want to see next time.